In this chapter, we examine the security model defined by the OPC UA specification and some of the basic security principles that will be supported by OPC UA applications. In this first module, we discuss the public key infrastructure and the management of the application instance certificates. This section provides an introduction to the components of the public key infrastructure. No OPC UA application may establish communication with another application or entity without first establishing a trust relationship. This allows the application to determine the identity and the validity of the other, as well as determining the protocols for exchanging and securing messages. The information required to establish this trust is contained in the application instance certificate. Certificates are the primary security mechanism in OPC UA. All certificates in OPC UA applications shall use the X509 version 3 certificate format. A certificate is an electronic ID that is held by an application and certifies the ownership of the public key by the named subject of the certificate. The application instance certificate identifies an instance of the application installed on a single machine. Each application instance will have a globally unique URI which identifies it. As applications may support multiple security profiles, they should support multiple certificates. The OPC UA specification states that an OPC UA application will, upon start, check for a certificate. If none is available, the application will generate a self-signed certificate. Further, each application shall permit the installation of a certificate that meets the security requirements of the system as required. A root certificate is a certificate belonging to a root CA, the anchor in a trust chain. The root CA has a self-signed certificate, so its trustworthiness must be established through another mechanism. For example, Microsoft distributes a root certificate with its operating system. A self-signed certificate is a digital certificate that has been signed with the subject's own private key. These certificates can be created by anyone and can be used in situations where the administrators of the UA applications are able to verify the certificates by viewing the contents themselves. The process for establishing this trust is carried out by the Public Key Infrastructure, or PKI. This is a set of roles, policies, and procedures needed to create, manage, distribute, use, store, and revoke digital certificates and manage public key encryption. All of the currently supported security profiles in OPC UA require a PKI infrastructure. A typical PKI is composed of the following entities. The Certification Authority, or CA, is an administrator or organization which is responsible for creating and managing certificates. It is usually a partially automated software product. The Certification Authority verifies that information placed in the application instance certificate is correct and adds a digital signature to the certificate that is used to verify that the information has not been changed. Each CA has its own digital certificate which is used to create these digital signatures. The certificate store is a persistent location where certificates and certificate revocation lists are stored. This is a disk resident file structure location, although Windows platforms do support a secure registry location. The certificate store contains a copy of the application's own certificate, the trust lists, which are lists of trusted certificates of both applications and CAs, and a list of untrusted or rejected certificates. The Registration Authority, or RA, is an entity that verifies user requests for a certificate and instructs the CA to issue it once the user is verified. The Validation Authority, or VA, is an entity that verifies the validity of a certificate based primarily on the certificate revocation list. The use of the VA allows for an offline CA, which is a good security practice. With the VA Online, the Online Certificate Status Protocol can be used to determine the status of the X509 certificate. And finally, the encryption keys. For asymmetric encryption, each application generates two encryption keys. A public key is distributed to other applications with which the originator wishes to communicate via the application instance certificate. Each application will also generate its own private key. The public key is used by the sender to encrypt messages, which can then only be decrypted by the paired private key. The private key is also used to sign messages, which also may be verified by the paired public key. It is very important that the private key be stored in a secure location, inaccessible to unauthorized users. If compromised, the private key must be replaced and a new series of certificates distributed with the newly generated public key. In this section, we look at the process for creating and installing an application instance certificate. The administrator installs the application on the required machine, providing the machine name or address and the organization name. Upon installation, the application generates a self-signed certificate. If the administrator deems that this certificate meets the requirements of the system, the process stops here. However, if the self-signed certificate does not meet the system requirements, the administrator shall request a certificate from the appropriate CA. The administrator shall provide the following information: machine network name or address, application name, and the name of the organization. Verification of the information within the certificate request can be accomplished by the CA or handed off to the RA, depending on the infrastructure that has been set up by the administrator. Upon verification, the CA will issue an application instance certificate that contains, among other things, the application public key, the application private key, and will be signed by the digital signature of the CA. The administrator then installs the new application instance certificate, replacing the old self-signed certificate. During the connection process, applications will exchange certificates which must then be verified before connection and communication can take place. If the certificate is not in the trust list, the certificate will be examined to determine the chain of trust for that certificate. If the certificate is self-signed, the administrator must determine if it is trusted by examining the contents manually. If the certificate is issued and signed by a CA, the certificate of the CA that issued that certificate must be found and verified. This carries on, establishing a train of trust until a root certificate is reached. In doing this, each certificate in the trust chain must be verified. These certificates will either be stored locally or contained in the original application instance certificate. If a certificate is revoked, if, for example, the private key of the issuer is compromised, the certificate is placed on the certificate revocation list. Any chain of trust containing this certificate is now considered broken. The CRL is therefore a necessary part of the verification process. Applications will also ensure that the certificate is valid. The process for this is well defined, including which actions to take upon detecting an error. Some errors will terminate the check and reject the certificate. Others will prompt the user to determine if they wish to accept the certificate as is. The criteria for this determination includes, but is not limited to, structure, signature, validity period, host name, and URI of the application. Once the certificate has been verified, it will be added to the trusted certificate list. The connection and communication process may now proceed. This is the end of this presentation. I will now hand you over to Gaurav, who will lead you through a demonstration of certificate management. Please click on the demo button to proceed.
In this demonstration, we'll see how the security in OPC UA works using the public key infrastructure. First, we'll look at the security policies supported by the Matrikon Flex OPC UA for codices and see how this can be configured using the Matrikon Flex editor in the codices IDE. Then we'll check the client's X509v3 certificate and go through the elements defined in the certificate which would be used to provide the public key information to the server. We'll then see how the codices security agent can be used for certificate management and use it to upload and delete the client certificates to the OPC server so that the server can validate the client authenticity during the connection process. To start with the demonstration, I will first start the Codesys IDE. While this is starting, we'll also start the Codesys control win from the sys tray. You can see now the Codesys control win is running. Once the Codesys is started, we'll click on the new project to create a new project for the including the Flex OPC UA server. We'll use the standard project template and give it a new name, for example, security, and click OK. So this using the standard project would create all the necessary elements required in the application, and we don't need to configure anything else. For the device, we'll select the Codesys control win3, and for the PLC programming, we'll select the structured test. Once the project is created, we'll click on the device, double click on the device, so that we can connect to the device by scanning the network. So you can see the device is present, and we can double click on it to make it as the active device. So once the device is identified and we are connected to the device, we will go to the device, right click on it, and add the Matrikon Flex OPC UA server to the project. We will use the same name which is specified and click add. So this will open a new window where you can configure the communication settings which should be used by the OPC UA server. So first of all, we'll get the host name from the device itself, and we'll use the port number as 4846 and the number of sessions are 5. And the next thing which we need to look at is the security policy. In this demonstration, we'll be using a security policy so that we identify how the security works. If you click on the security policy, we can see a list of security policies here. Each of these security policies define a set of algorithms which should be used by the client and the server to encrypt the data which is communicated between the client and the server, and also sign the data to provide authenticity as well as data protection during the communication. Each of these policies are defined in the OPC UA specification, and depending upon the application profile the server is supporting, it has to select the security policies. The server can also provide multiple security policies with different endpoints. So now we'll be selecting one of these security policies. So for example, I will be selecting basic 256 SHA 256. So the main idea of having multiple security policies is to, or having different types of security policies is to have a different level of security. So depending upon what kind of algorithms or what kind of security you select here or security you choose, the server would use different algorithms, as I said, and each of these algorithms have a different level of security. So for example, the basic 256 256 is one of the strongest algorithms as it uses SHA 256 based encryption, which is considered to be quite strong and requires a lot of processing power before it can be broken. So we'll select those. So once I click on the login, the new configuration for the OPC UA server would be downloaded to the Codesys control Windows container. And now once this is done, we can see that the Codesys container has started in the stop mode. We can click on the start button to start the application server on the Codesys control. Now what I'll do is I'll go to the start menu and start the Wireshark so that we can see analyze the packets. And I would, as we selected the OPC server to be started on all the interfaces, in the list of interfaces I will select all interfaces. For starting the capture, and then I click capture. Once this is done, I will also set the OPC UA filter so that we only see the OPC UA frames. Once this is done, I will go and start the Matrikon OPC UA Explorer. So once the OPC Explorer is done, I will click on the add new server so that I can discover the server, and I'll use the custom discovery and give as the username as the host name as localhost and the port as 4846, which we configured in the Matrikon Flex editor. So once if I do a search, this should perform a custom discovery. You can see here it tries to retrieve the servers from the provided discovery URL, which is there, and it is able to identify. And if we expand, you can see that now the Flex OPC UA server for Codices provides an endpoint with a basic 256 and SHA 256 algorithm based endpoint for the communication. And if you go back to the Wireshark and see the endpoint response, you can also see this or in the endpoint response message. So if you expand the endpoints here, you can see it has provided the application description along with the server certificate, the initial the server certificate to server certificate which should contain the public key of the server, and also the defines the message security mode, in this case sign and encrypt, along with the security policy URI. So as you can see, it's the basic 256 SHA 256 which we specify. Now going back to the Matrikon OPC Explorer, we can try to communicate or connect to the OPC server. So I'll give a session name as security, and I can try to connect now. So now we can see that when we try to communicate with the OPC server in the logs, we can see that it failed due to bad security check fails error, and the OPC Explorer also gives us the information that we have to check if the OPC Explorer certificates are uploaded to the server or not. So in this case, since we haven't uploaded the certificates, the server does not allow the client to communicate to the server, because it does not know the authenticity of this client, and server does not trust this client to be able to communicate. And for this we have to add the OPC Explorer certificate to the trusted list of certificates in the OPC server. If we switch back to the Wireshark and see the messages as well, we can see that the Open Secure Channel message is created with the client certificate, which along with the security policy URI. And since the server does not trust this sender yet, it rejects the Open Secure Channel, and you can see this by seeing the error message. So server responds to this by saying by sending bad security checks failed. So to resolve this, what we can do is we can, like I said, we can use the Codices security agent. So for that, I will first log out. So we can manage the certificates of the client in using the Codices security agent. So to open the security agent, we can go to the view, and then we can click on the security screen. So this will open a new window where you will be able to see a list of users, project and devices to which the certificates can be issued or certificates can be created. So for this case, we will be using the device. So and what we will be doing is we will upload the OPC client certificate to the server. So for that, first we'll refresh and see what are the certificates already available. So we would be able to see the certificate store itself on the device. So there would be the certificate of the server in this case, which is the Codices Win certificate. Then we have a list of trusted certificate. As you can see, there is no certificate yet. So that's where the OPC Explorer was not trusted.